Whether you are an expert in the machine learning domain, or if you are just beginning to learn about machine learning and neural networks, you must surely have heard of activation functions that create the nonlinearities in the deep neural networks. These are some of the familiar names in this domain, for example, sigmoid function, rectifier linear unit function, its leaky versions, etc. I am planning to go over the details of all of these in the future videos, but for now, I assume that you are already familiar with these specific activation functions, and I want to talk to you about Mish, which is another activation function that was recently proposed in order to enhance the performance of deeply connected neural networks. An extremely short summary of this paper is that Mish is an activation function defined as x times hyperbolic tangent of soft plus of x. And it proposes some advantages such as increased convergence rate and more robustness to the alterations in the input due to noise and things like that. Additionally, it is possible to implement it with efficacy as well, which therefore makes it reasonable to choose this over other activations such as ReLU in many cases. You can also find it in the official PyTorch package as torch.nn.mish. Now let's get into more details in this paper. This paper includes a lot of experiments in which they validated Mish empirically against different benchmarks and different combinations of architectures and activation functions. The results indicated that, in addition to the usefulness of data augmentation in many cases, Mish outperforms the famous leaky ReLU on YOLO version 4 with this type of backbone, and with the performance metric of average precision by 2.1% in MS-COCO, and ReLU on Resident 50 on ImageNet 1K and top 1 accuracy by 1%. So all of these shows that this type of activation function is very useful. There was also this Swish family of activation functions, which was found using neural architecture search. Now, Mish is kind of a result of systematic analysis of what kind of features and characteristics makes those types of activation functions useful, and then Mish was designed based on those. And the idea is to propose an intuitive understanding on how the first derivative behavior may be acting as a regularizer, and it sort of helps the optimization of the deep neural network and therefore results in the good characteristics that makes Mish a powerful activation function. Now the code is also released, but again, you can find it in the PyTorch package as well. Now let's go to some of the basics. First, paper starts with the definition of the activation function, which is nonlinear and pointwise functions that are responsible to introduce nonlinearity to linear transformed input in layer of a neural network. So assuming that you have like L layer neural networks, you know that this sort of W times X plus B with weights and biases applies. So if you do not have that linear component over here, and if you stack multiple of these together, you would end up having some sort of a Wx plus B prime. So eventually the entire thing would become a linear approximation, which you don't want. Therefore, these types of nonlinearities help managing that and help covering higher patterns of higher complexity. Now the paper writes it in this form, which is G applied to this kind of like weight and biases. And in the early literature of machine learning, the sigmoid and hyperbolic tangent functions were the ones that were mostly used. Later on, there was the rectifier linear unit, which is less probability inspired and unsaturated, and it was a piecewise linear function. So ReLU became very famous and became more relevant. It showed better generalization and it showed improved speed compared to the sigmoid and tangent hyperbolic functions. But it wasn't without its own disadvantages, the main one being the dying ReLU problem. Given the shape of the ReLU function, this being the zeroth axis, collapsing the negative inputs to zero could cause the gradient information loss, which was basically the big problem with the ReLU. And in order to remedy that, there were challenges and there were ideas such as creating this type of non-zero reaction to the negative inputs, therefore not losing gradient information on those rather than just like damping it and things like that. And it resulted to leaky ReLU. There was like exponential linear unit. There was other things such as a scaled exponential linear unit, and so on and so forth. Then there was another activation function which is called swish, which was found as fx times x times sigmoid of beta times x. So beta is a scaling factor. One thing to kind of, let's start with this, is that this thing here, meaning that multiplying x itself, non-normalized version of the input by the entire thing, this is called self-gating, and apparently it's one of the useful things in Swish, which is also apparent in Mish as well. So that's one of the key aspects of this activation function. Now, Swish, after it was found, it showed strong improvements in the results compared to the other activation functions known before. It had the smooth continuous profile and resulted in better information propagation compared to ReLU. Now again, the Mish activation function, which is proposed in this paper, is defined as x times tangent hyperbolic of soft plus of x. And they validate that Mish tends to match or improve the performance compared to Swish, ReLU, Leaky ReLU across different tasks in computer vision. In the theoretical analysis and research into activation functions, the important properties are non-monotonicity, ability to preserve small negative weights, and a smooth profile, meaning that you don't have points in which you cannot find a derivative. And for instance, to have other types of activation functions such as Gaussian error linear units, which is the activation function that is actually used in GPT-2 and GPT-3, many transformer-based architectures. Now, Swish was an activation function which was found by the neural architecture search, which is a methodology discussed in this paper, over the space of nonlinear functions by a controlled search agent. So the way this neural architecture search worked was that you had this RNN controller that was acting as an agent, and this agent would generate new candidate functions at each step, and it would be done to 10,000 steps, which these steps were evaluated on Cypher 10 classification task using a ResNet 20, defined with the candidate function as its activation function. Basically, iteratively, it would go through different types of options for the activation and figure out the best one. Now, Swish was found empirically like that. Now, the design of Mish, they mentioned, is implemented by this work that was performed by Swish. And it was the result of systematic analysis of the characteristics that make Swish so effective. For example, the self-gating thing that we discussed. To validate it, they had a six-layered deep CNN architecture, and they basically validated it on different benchmarks. The networks that they had were trained for 50 epochs with RMS prop optimizer, and they figured out that Mish was actually performing really well. There was also x log 1 plus hyperbolic tangent of EX, but it resulted in some unable cases which led to divergence. Now, what makes Mish special? First, let's find the derivative of Mish. As discussed, Mish is defined as fx, so fx being the Mish activation function, is defined as x times, again, this is the self-gating, so x times hyperbolic tangent of soft plus of x. Now, note that soft plus of x is defined as 1 divided by beta ln 1 plus x beta x. Okay. Now, one question you might be having is that what exactly is the soft plus? So consider the ReLU case. This is 0, this is x, this is y. And for the ReLU, you had this sort of curve. Now, the idea is to kind of make it softened, meaning that you want to have something like this, which gives you essentially this soft plus. Now, if you look at this, you can see that in the bigger x's, let's say x is like a high value, this 1 becomes kind of negligible compared to this x of beta x, and then this would be kind of dragged out of the logarithm, and therefore you would have the x as the output. So therefore these cases would essentially be very similar to the x. Now, what would happen is that on 0, you would have 1 beta times ln 2 as your result. And when you go to negative infinity, this becomes 0, which therefore ends up with ln of 1, which in limit, this part on the left side also approaches 0. So soft plus is basically a softened version of ReLU, a smoothened version of ReLU. Now back to our discussion, let's look at this and call it like this. So let's say you have x, Let's say tangent hyperbolic we denoted as G, and soft plus we denoted as H. Now, if we go down and try to kind of rewrite it, we can see that fx becomes x times g of h of x. Now, what we are interested in seeing is the derivative of f with respect to x, which in turn would give us, first of all, the derivative of x times the g hx, which is g hx itself. You could also write it as fx divided by x, plus x times the derivative of this part, which becomes h prime of x times g prime of hx. Now let's expand this. We know that g of x is the hyperbolic tangent of x. I'm assuming you are familiar with hyperbolic functions, so if you're not, just as a recap, the hyperbolic sine of x becomes x of x minus x of minus x divided by 2. The hyperbolic cosine would be like this. You could use this to show that this equation holds, and you can divide both sides by this, which 1 divided by hyperbolic cosine of x squared is equal to this. So this is just important because of, rewriting what we have to rewrite. So back to the discussion, gx was hyperbolic tangent of x. We know that the derivative of this becomes 1 minus tangent hyperbolic of x. You can verify that easily. And therefore, the g prime of hx would be 1 minus hyperbolic tangent of soft plus of x, which, given this finding, becomes second hyperbolic squared of soft plus of x. Now, as for the h of x, if you consider the derivative with respect to x, you would have 1 divided by beta times beta x beta times 1 divided by 1 plus x beta, which, if you divide, so betas can get cancelled out, and if you divide this entire thing, both numerator and denominator, by x of xb, you would end up with the sigmoid of x beta, which is defined as 1 minus x buff, 1 plus x buff minus xb. Now, you have this as well. So you could rewrite it as this. So the derivative of Mish becomes fx by x plus x sigmoid of x beta second hyperbolic squared of soft plus of x, which basically means that in this case you have the swish x, which was defined as x times sigmoid, which therefore means you have the swish activation function here and a delta x, which is going to play a role here. So with this connection established, they speculated that this delta x parameter is going to act as a preconditioner, or like a gradient smoothener. Now, this preconditioning has been discussed in the optimization related problems before. The idea is that you have like this loss landscape, and kind of like you have like this, for example, symmetric positive definite matrix. You apply it to modify the geometry in order to kind of increase the rate of convergence and to make it easier to reach the optimal point in the landscape and on the manifolds. So intuitively, they mentioned that precondition makes the objective function much smoother, makes it easier to optimize it. And delta x is going to mimic the behavior of a preconditioner. That's essentially their conjecture as to why this is the case, and why one could try to interpret why Mish outperforms Swish in many of the tasks. In terms of similarities between Mish and Switch is that they are both monotonic, smooth, and they do preserve negative weights in a small fashion, but they don't have the dying ReLU problem. And if you, for example, have a neural network that is powered by, let's say, ReLU compared to Mish, and if you visualize the profile of these results, you can see that there are a lot of smoother transitions when Mish is involved compared to, for example, ReLU. Now again, this picture, let me bring it here, is the output landscapes of a 5-layered randomly initialized neural network with ReLU and Mish being visualized. The idea was passing the coordinates to a 5-layered randomly initialized NN, which outputs the corresponding scalar magnitudes at those positions, and then this output landscape is going to be shown to have a lot of transitions, sharp transitions in ReLU, meanwhile having smoother transitions when Mish is involved. Additionally, they also focused on the loss landscape as well, which is demonstrated in Figure 4, which we'll talk about in the next parts of this presentation. Now, similar to Mish, again, similar to Swish, Mish is also bounded below, and it's unbounded above with certain ranges, and also has this self-gating property, which, again, as we defined, was the non-modulated input being multiplied by the output. And given the fact that it's not going to be zeroed out when the negative values are involved, Mish eliminated by design the preconditions necessary for the dying ReLU phenomenon that was the main issue with the ReLU. It is also continuously differentiable, which is a very preferred property. Showing the loss landscapes here, you have the ReLU here, and then you have the Mish, and you have the Swish activations. And you could see that kind of visually, the landscapes for ResNet 20 when Mish is involved is much more smoother and conditioned compared to the ReLU and Swish counterparts. Right, in terms of kind of good properties, first of all, there's some investigations on the overfitting. So if you consider a deeper neural network, each layer initialized with 500 neurons with residual new units, because you want to have basically an analysis over the depth of the networks, they use batch normalizations and dropout and other things. Now, they kind of detail out the optimizations that they have used and everything else here. The key thing is that they show that after 15 layers being involved, there will be a sharp decrease in the accuracy, whether Swish is used or ReLU, but Mish maintains significantly higher accuracy compared to those, which is the case when optimization actually becomes difficult. And it was validated in the other benchmarks that they tested it on as well. In other words, and another thing was the robustness of Mish when you encountered noisy inputs, which they tried it by basically having MNIST data corrupted with additive zero-centered Gaussian noise. Looking at the picture here, you have number of layers on the bottom, you have testing accuracy on the top. You can see that ReLU consistently drops, Swish drops more, but Mish relatively saves the performance. In terms of standard deviation of input Gaussian noise and test loss, you can see that the red one, which is Mish, exhibits a smaller test loss, which means more robustness to this input noise. And then again, we have the comparison between Mish and Swish activation functions in terms of test accuracy. You can see that Mish consistently outperforms Swish in these different cases. So again, in the C, different types of initializations are involved, and initializing the network actually is going to play an important part as well, but you can see that it is safe to assume that Mish actually is going to improve better regardless of what kind of initialization is being used. You can see some of the benchmarks detailed out here. You can see that Mish is going to consistently sort of outperform everything. You have Cypher 10 over there, you have this over here, so you have different architectures, you have different activations, and you can see that it's kind of regardless of the architecture, activation, initialization, Mish seems to be outperforming others. And you have additional benchmarkings confirming this point as well. In terms of the computational costs, they focused on a CUDA-based implementation in order to optimize Mish, and you can see that based on the results that they report, Mish is actually optimal to run as well. Which concluded the discussion that their implementation of Mish, which they call it Mish CUDA, is a pretty good thing to use in deeply connected neural networks and computer vision, and possibly beyond. this concludes our discussion on the Mish activation function. Thank you for watching this video.